Janssen, this energy will be deposited within some finite distance of the injection. And so in practice, this will lead to an inhomogeneous recombination history, and this will lead to CMB non-Gaussianities. And from simple estimates, I think this could be stronger limits than the power spectrum. In the last few minutes, I'll talk about gravitational waves. So as you pointed out, obviously, some people asked whether LIGO detected dark matter. Julian and I were part of these people. But I want to ask the question of whether it actually rules it out rather than detect dark matter. So what we did in this paper led by Simeon and Bert is as follows. So this is formation mechanism for primordial black hole binaries in the late universe. So the process is very similar to radiative recombination, except that you don't have a time-varying electric dipole moment, but you have a time-varying quadrupole mass moment. So if you have two point masses that zoom by each other, this gives you some time-varying quadrupole moment. This radiates gravitational waves, and there is some cross-section for which they actually become bound. And you can compute this. It's a very nice homework problem for a GR class, and this gives you some scaling as v to the minus 18/7. From this, you can just compute the merger rate per unit volume. So the number density of black holes times the cross-section times velocity. So and you integrate over the halos times the halo mass function, the abundance of halos, basically. So that's what we did in this paper with Simeon and Bert, and we got some number which was around 1 per gigaparsec cube per year. If primordial black holes made all of the dark matter. Now, one of the ingredients is first the number density of halos and the abundance of halos, and here we made some, we just extrapolated the standard particle dark matter halo mass function. What we showed in this paper is that, well, you should account for Poisson fluctuations, which will affect the halo mass function at small scales, but there's some kind of PBH miracle, and the rate that we get is basically the same. However, this is one formation mechanism. There's another formation mechanism in the early universe, which is in fact much, much more efficient. And so the idea is as follows. This was put forward by Nakamura et al. In 1997. So on small enough scales, primordial black holes are essentially randomly distributed. On large scales, they must follow the perturbations of dark matter if they are to be the dark matter. But on small enough scales, because of their discrete nature, eventually they're randomly distributed. So you may have pairs which happen to be born close enough that they will decouple from the Hubble flow deep in the radiation era, and then they will, in principle, they would just fall down straight head-on onto one another, but they're going to be torqued by the other primordial black holes, so they will form some eccentric orbits, and then they will slowly spiral through emission of gravitational waves, and merge throughout the cosmic history, generating some gravitational wave background, but also merge all the way to the present time, generating some mergers that could potentially be detectable by LIGO. So if you fold everything together and you can estimate all of these steps, in particular you can estimate what is the initial probability distribution of orbital parameters when these binaries form. Then you can compute the merger rates. So if primordial black holes were all of the dark matter, what you find is the merger rates. So these are the LIGO. So this is from 2017, so this may have changed a little bit, but basically those are upper limits. In some cases, you have actual detections. Yes?
So these PPH are large enough so that their mass isn't evaporating at
Yes, yes. So this is, the evaporating ones are those whose mass is less than 10 to the 20 grams or something.
40. 40.
That would be evaporated by 2. Yes, okay, evaporated by 2 days. Yeah.
Asteroid
right.
masses.
Right. But then you could have, I didn't mention, but those who are less than 10 to the 20 or 17 grams, I don't remember. Those could still evaporate, have some signatures due to evaporation, even though they still have not fully evaporated. So yeah, those don't evaporate. They're basically just like normal black holes in terms of their masses, just formed early. So if you turn this around, you see that this merger rate predicted is like orders of magnitude more than LIGO. So in fact, LIGO, rather than maybe having detected dark matter, could still have detected primordial black holes, but they would have to have a much smaller fraction than being 100%. So you could turn this around and set some upper limits on the abundance of dark matter. The reason I call them upper potential limits is that, again, I think one should be as careful with primordial black holes as with any other dark matter candidates, and can only call it a limit if it's a limit beyond any reasonable doubt, and there are still some reasonable doubts in this calculation. So what are the uncertainties? So first of all, the initial spatial distribution of primordial black holes. So for a while there was this notion that that came from a paper by Chisholm that had some mistake in it that concluded that primordial black holes would be born in very dense clusters. And I showed that this was not the case last year, and this was confirmed by a few other authors. But still, the question of initial clustering of primordial black holes is an interesting one, and I don't think it's fully, completely resolved. But at least they're not, in principle, born in very dense clusters. The other point is, what is the initial distribution of orbital parameters? So the way we've calculated this is by assuming that you have some, say, closest neighbor pair, and then you have the other black holes which don't really cluster until much later on. But in practice, they will start clustering, and if this pair is part of some overdense region, it might, already form some proto-halo rather early on, and this could affect the initial distribution of orbital parameters. So Orbital did some 70 body simulations, and what they found is that the simple analytic approximations that we use are self-consistent only if primordial black holes are a small fraction of dark matter. They're not self-consistent otherwise, but it doesn't mean that they're wrong, but at least they're not fully self-consistent, and one should have a more careful look. So the picture that you should have in mind has these limits that I showed. Really, one should truncate them here until one has checked more carefully what happens when primordial black holes form most of the dark matter. One thing that I worry about a lot is the following. So this is showing as a function of the fraction of dark matter primordial black holes, the characteristic formation redshift, which is, as I was saying before, typically of order 10,000 to 100,000. So these binaries form very early on. They form with some characteristic eccentricity. So this is square root of 1 minus eccentricity squared. This is a small number, so these are highly eccentric binaries. So these are almost head-on binaries. And so those are very easy to torque. And so the question is, between the time they form bound systems around 10 to the 4 and the present, do they actually survive, or do they get significantly torqued? So there are several effects that could matter. For example, if primordial black holes are not all the dark matter, they could form some dark matter halos, which could affect them. These people looked at this and they found that this is not a significant effect. You could also have a binary accretion disk, which could torque the binary. And this is, I think, still unclear exactly whether this would matter or not. And a purely gravitational effect would be the effect of the first nonlinear structures, which could, again, significantly torque those binaries. We made some analytic estimates in this paper. We found from analytic estimates that they should be negligible, but one thing that I like to do is to check it numerically. So my postdoc, Derek Inman, motivated by this, but then I think we could have also other applications, has implemented some small-scale 30 kiloparsec cube simulation of mixed dark matter, where some of it is made of primordial black holes and some of it is made of particle dark matter. Run them from redshift 1 million to 100, just to see. This is just a nice visual of the simulation. So if this was a standard pure particle dark matter simulation, by redshift 100, basically nothing would have happened yet, because nothing would have been clustered. So what you see here is the clustering as a result of just Poisson fluctuations, just the random density fluctuations in this grainy, this discrete dark matter fluid, which is primordial black holes. So just to illustrate more, as you crank up the fraction of dark matter in primordial black holes, you crank up the graininess of dark matter, and you will have, by redshift 100, you will have formed already significantly relatively large halos if all of the dark matter is in primordial black holes. As opposed to if you had almost no dark matter and primordial black holes, you would just have this rather smooth universe, which is the standard picture that we have today. So one of the things I'll just leave to the audience is, could this influence the formation of the first stars, for example? I'm not sure whether this would or not, but I think it'd be interesting to think about this. So there are several things we extracted from this paper. For example, I would say that we checked that the mass function matches the generalized Press-Schechter mass function, which was calculated by Epstein in the case of Poisson distribution. The one result that we checked was that the nonlinear velocities would not affect CMB limits. But as I said, the main thing that Derek will be working on now is to try and extract the tidal field from the simulations and figure out whether primordial black hole binaries would be disrupted or not before the present time. I think I have gone over time. This is designed to leave you with my conclusions. So in the first part, I briefly summarized CMB physics. The one takeaway message is that the way that the universe recombined plays a key role in CMB anisotropies, and we're working on a code which will be not only very accurate, but also run in 10 milliseconds and should become the standard for CMB analysis. I told you how CMB spectral distortions and anisotropies could set limits on dark matter particle properties, and I think that it's time to develop a bit more comprehensive theoretical framework going beyond a simple ideal fluids approximation. And lastly, primordial black holes are, I think, still a very interesting dark matter candidate, or interesting thing to think about, and their signatures still remain to be fully